represented algebraically. Just if it's a linear function, right? It does not matter what representation we're looking at. What do we know about linear versus exponential?
Okay, linear, they have straight lines.
Linear has straight lines. What else?
Exponential got curves or whatever.
I feel like we talked about something yesterday that also had straight lines versus curves.
Yeah, same thing, I think.
Was not discrete and continuous. Say it louder. Arithmetic and geometric. Didn't arithmetic also have an additive rate of change?
Yeah.
Yeah?
Mm-hmm.
And geometric had a multiplicative rate of change?
So you can say that's a linear function to the arithmetic sequence.
Well, okay, so let me say it this way. You have a square, right?
Mm-hmm.
Meaning that all the angles are what?
Equal. 90 degrees.
90 degrees, which does mean the measures are equal. Okay, so if you have a square, all the angles are 90 degrees, and what else is true?
It's all right angles.
Yes, so we talked about the angles. Now all 90 degrees, what else?
All the same size.
All the sides are the same
Like,
length, right? So that idea of a square, does that fall into, do some of those ideas fall into the idea of a rectangle?
yeah.
And just some,
Some, which ones?
the right angles.
The right angles, right? So that means that every square is a rectangle, but is every rectangle a square?
Nope.
No.
Is it too long?
Okay, so it's the same idea. Well, a rectangle doesn't always have to be too long. It just, a square will always be a rectangle. A rectangle can be longer than it is wide. It doesn't have to be though. Okay. Similar thing with a linear function and an arithmetic function. We're going to talk about the differences between them in a second. But the idea is that an arithmetic function is a type of linear function. So you can think of an arithmetic function as
Square.
the square, the linear as being the broader category that arithmetic falls into.
And then they're all squared.
So instead of just rewriting everything, I mean, that would probably be a helpful visual, but we can actually do that somewhere else on this graphic organizer. But my point is this. Instead of rewriting everything, what are all the details about a linear function that we already know, that we've already written somewhere else?
Common difference.
Didn't we write a whole bunch of information that would also, that we could say is also true about a linear function?
Yeah.
Where did we already write information about it?
Arithmetic sequence.
Arithmetic sequence. So I would just make a quick note right here. See all information about arithmetic sequences. Now, linear functions are a little bit different, but for the most part, all the information about rates of change and everything else is going to be true for an for a linear function, because they're very similar. Right, so and I will point this out, that is not, I'm not saying here that a linear function is the same as an arithmetic. What are we comparing in this case?
Arithmetic and linear.
Linear and exponential functions, right? So everything that was true about an arithmetic sequence versus a geometric sequence is also going to be true for a linear function versus an exponential function. There's a different section later for us to compare linear versus arithmetic. Does that make sense? Right? So, well, like I said, see all information about arithmetic sequences because they're very similar to compare, let's say it that way, to exponential. And so what are we going to look at for information to compare exponential to linear? What type of sequence do we study that is very similar to an exponential?
Geometric.
Geometric, right? So if we compare arithmetic and geometric, we're comparing linear to exponential. So examine geometric versus arithmetic for key differences. In exponential versus linear. Okay. So instead of rewriting all that information, we're going to look at arithmetic versus geometric to know the differences between linear and exponential. All good? Jeffrey, we good? We got that down? Jeffrey, do you want to move up to group 5 so you can more easily see from back there?
Is it warmer?
I don't know.
It's hot up here.
Yeah, it's pretty hot.
You
They think it's
that's
warmer.
good?
I'm burning up.
I'm sweating.
No. Do we have drinks in my class?
I don't know where that one came from.
Mona.
I'm gonna wipe it up, but I don't know where it came from.
Mona. Alright. So at the beginning of class, before y'all came in, I passed out your retest. They weren't pretty, y'all. I read through all the notes that you made about what you said that you did to study. But the evidence was not there that we studied for this, guys. I specifically designed this to be easier than the 9 weeks exam you took last semester, and we definitely did worse on it. What happened?
We were
Couple
sleepy.
weeks off.
Couple weeks off?
Yeah, I forgot everything after that.
Y'all think it's problematic that we forget everything we've learned in the span of 2 weeks?
Sometimes we
Okay,
forget in like 3 days.
Don't you think that's kind of problematic?
Yes.
Yes. When we learn stuff, we need to learn it deeply and we need to learn it well. This is a consistent issue with why students struggle mathematically from year to year, from semester to semester. It's because we don't learn it as deeply as we need to. Caroline, can you please keep an ass up? Thank you. This is why I ask you to talk more. The more you talk, the better you'll learn it. The things that you talk about and you engage in and you discuss with your friends, you remember them pretty easily, don't you? Most of the time? I mean, like, I don't know good examples for y'all, but I assume a lot of y'all like to talk about different TikToks and you remember them for 5 ever, even though it's like a 30-second clip. Is that fair to say? Okay? The things you talk about, the things you discuss, the things you engage in, those are the things you're going to remember. But you need to spend time thinking about them. That's the common thing amongst all these ideas. The things you learn well are the things you think about. The things that you discuss.
Get that for me. Thank you. You're so kind.
Okay? I need y'all talking more. Discussing these ideas. Taking notes and actually studying as well. This is the last time I'm going over a lot of this information because it's honestly the 5th, 6th, 7th time. We're going to record all this information. If you need this information in the future, you have it on your graphic organizers and there'll be videos online. I will be bringing in the MacBook parts later this week so that we can learn how to use Simbo Lab, a really powerful resource online that there's actually an app for. Learn how we can use Desmos, learn how we can use Khan Academy to help our learning. Because apparently we are very hesitant to come into the free tutoring that I have for you to learn. So I'm at least going to help you get the resources you need outside of class.
Do you be like going live? You know what I mean? Like going on Zoom or whatever. When you had your tutoring. That way you could like join in.
No, I have tutoring here at the school for free.
Well, some of us can't like make it back home after a certain time, so can you just do it on Zoom too? Like you, just like how you be recording your class.
When would you want me to do Zoom?
When you do tutoring.
7:20 to 7:55, 3:15 to 4 o'clock, like it
Yeah,
says
in
in
the
that.
evening. Yeah, in the evening.
The afternoon?
The afternoon.
Why can't you stay after school for the afternoon session? If you're already here, I don't understand.
Because then I'm gonna have to get a ride back home unless you can take me home.
No, I mean, I don't have internet access from my laptop, so no, I cannot do the tutoring. And if no one stays for tutoring, I don't stay here. What would be the point of me sitting around until 4 o'clock if no one's here to get help?
Well, you're right.
Okay? If a student wants to stay after school, I'm more than happy to be here. If a student wants to come before school, I'm more than happy to be here. But I'm also going to try to help you develop the resources you need or understand how you can use different resources online to help you out. Everybody, when they walked into class, they got a paper for release form. Okay? Throughout the year, I've been recording the stuff up here, but I haven't been recording students per se. Might hear someone talking and things like that, but that's about it. And that's just for our class YouTube to be able to post things online. This, though, is because I'm working on something called National Board Certification. It's a certificate to indicate that I'm a nationally recognized math teacher, that I am trying to help my students become better and constantly trying to grow myself, all those things. As a part of that, I have to show evidence for what I'm doing for my students and how I'm trying to grow and develop and things like that. And so I'll have to video different parts of the classroom at different times. And so please understand, if you do give consent, the videos are not about analyzing you, they're about analyzing me. Plain and simple. It's not about anything other than, one, I will be analyzing myself to figure out how I could help students better. But two, when they look at my videos I submit, they'll be analyzing me. But in order for you to be a part of the video, I need you to fill out a release form. Now, you can choose not to give consent, that's fine. I need you to at least give this to your parents and return it to me filled out. Please do give consent so that you can be a part of the video. If I choose to say, man, y'all had a really good discussion, I feel like this is really indicative of how I teach overall. What are you going to say, Mona?
Do you have to have a parent sign it? What if you like grown?
If on the back it says, an adult student, I am the student named above and am more than 18 years of age, I have read the letter, blah, 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 blah. So if you've turned 18, I think you can sign this, right?
Yep.
As long as you're a day over 18. Okay?
Or an hour.
Or an hour, a minute, a second. As long as you're over 18, okay? I will also say, very simply, free homework grade if you get it turned in.
I'm gonna go and do this now.
I'm not doing a test grade. The simplest homework grade you've ever had.
Well, it's gonna take me a few days.
What's our intern's name in the back since we're trying to get to know him?
Mr. Lippum.
Mr. Lippum. All right, so McKay said it today. He is not allowed to say it tomorrow. Everyone else needs to be able to respond tomorrow.
Is that an extra homework grade?
No. You learned a name.
Like when you're fishing.
All right,
English grade.
let's look at our objectives quickly. Who read objectives yesterday? I think Mona did, right?
Yeah, I read all of them.
You read 2. Who else read yesterday?
I did.
Both of you? You weren't here. McKay, you did? Anybody else? Okay, Caroline, you want to start us off then?
I read.
Oh, you
read
did read. Donovan, you did?
It was me, McKay, Mona.
I say, I think you did, Donovan.
Yeah,
Donovan did
I
too.
sure did.
Cause I read
Donovan
before,
did
but then you
read.
told me.
Yeah, he read the one with the least words in it.
Oh, this third one down here?
Yeah.
You almost read the fourth one.
So then, Caroline, you must not have read.
Yes, I did, because Mona said that she couldn't hear me.
Oh, that's right.
Uh-huh.
Alan, start us off then.
The first one,
Yep,
I can differentiate continuous from discrete scenarios/models.
okay. So Donovan, what does the word differentiate mean?
I remember.
You forgot? Well, we need to pay attention then.
Can tell the difference.
So differentiate, we can tell the difference between a continuous and a discrete model. Gavin, can you read our second one for us?
I can write the recursive and explicit equation of linear and exponential functions.
Okay, so writing the equations of functions is a important skill, which is why we have this graphic organizer. Jeffrey, can you read our third objective right here?
Wait, is it blue thing you have to go in there?
Which one?
This third one.
Oh, I can write the domain of functions.
There we go, we can write domains of functions. That is something from 2.1 to 2.2 that we do need to develop our skills in. And Key Anthony, can you read our last objective for us?
I can write a linear and exponential equations to identify parameters for the factor of a linear and
Okay, so this, one at the bottom, I will say, the idea of arithmetic and geometric means is something that we have struggled probably the most with. But that's because we don't use the principles that we know to apply. So we're specifically going to work on writing linear and exponential equations, not functions per se, but equations. So meaning, in that sense, only one variable, not two, to identify those common differences and factors. So last night I asked you to do recursive and explicit equations. So we should have some information here. A lot of us already had a lot of the really important stuff. What should we have under recursive? What's the overarching ideas?
Oh, okay, okay.
outputs
You can be talking.
Relates current outputs
To the previous output.
to previous outputs. How do we algebraically indicate a current output versus a previous output? Which one's the, okay, so which one's f of n, current or previous?
That's the current.
Okay, so f of n is the current. And what would the previous be? F of n minus 1, right? Doing the n minus 1 tells me to do 1 before n. When I write a recursive equation, do I just need the current and the previous? Is that it?
Always need some starting point.
We always need some kind of starting point. Okay, and for the sake of everyone being on the same page, the way I've started writing the starting point is f of a equals b. Meaning if the input is a, the output is b, okay? Now, I do want to point this out. Actually, I'll come back to this. I do want to look at arithmetic versus geometric and linear versus exponential with this. But what's the overarching idea for an explicit equation? We always multiply with an explicit?
Wait, never mind.
I believe there could be some multiplication, but is that the point of an explicit
I was
equation?
looking at the wrong one. Relates to inputs and outputs.
Okay, so recursive relates inputs. What do we use for inputs?
Hey.
It was the input here, but usually it's a value. What variables do we usually use for inputs? F of n is the whole input? I heard no.
Yeah.
Why not, Anthony? You still think it's no? Do you know why? Who agrees with Anthony, I guess, that f of n is not the input? Rowan?
I do, because I thought f of n was you said an input. I
Yeah.
thought f of n was an output.
Oh. Is f of n the input or is it the output?
Yesterday you told me it was output.
Well, I'm asking. McKay thought that f of n was the input. Key Anthony disagreed, and you're agreeing with Key Anthony.
McKay is wrong.
Just because you say it must be true, right?
from what you told me yesterday and from the information he gave,
Okay, let's
it
get,
sounds incorrect.
let's try to develop a little bit more evidence. Instead of just saying someone's right or wrong, and this is part of the issue that we have in life right now, is people just want to say you're right or wrong without backing it up. We need evidence. If you think f of n is the output, what do you think the input is?
What is,
Huh?
you do know.
Anthony, you think the input is what? N. Well, what's the thing on the inside that we could plug into? The N. So the input would be,
Oh my God, my head hurt.
what's the input? Okay, let me create an example. F of n is equal to 3n plus 2. What could I plug in for? N? What do you want to plug in for n?
1.
Okay,
Sure.
so n is going to be a 1. So 3 times
1
1.
plus 2.
Okay, so you see how I'm plugging in for, plugging the 1 in for the n, right?
Yep.
So I plugged into the,
Someone
N.
was right.
and so when I plugged in 1, what did I get out?
5.
So n was 1, f of n was,
5.
so what is my input? Is it the n or the f of n?
The input's the N, and the output would be 5.
Which is,
Yeah.
we go with that?
Learning.
You go with that, McKay?
I thought f of n is the same thing as n.
No. So when I say f of n, the n is what I'm plugging into. Notice how the 1 took the place of n? Because n is equal to 1. You good with that?
Yeah.
So when I plug the 1 in, 3 times 1 is 3, 3 plus 2 is 5. So plugging in 1 gave me out a 5. So n is what you plug into, f of n is what you get out. Notice, and this is an important language over here, that some of us are apparently skipping. The recursive relates the current what?
Output.
Outputs. F of n is an
Input.
output. Isn't it?
Yes, disregarded.
To the previous output, which is f of n minus 1. If you have that f of, that function notation, you're dealing with an output. Notice right here when I say f of a equals b, in that case n is equal to a, f of n is equal to b. So if I plug in a in, I get a b out.
Oh my God, it's cold.
It's not stupid math. We got to learn this a little bit better. It's okay. Instead of leaving it in your notebook right now, why don't you take it out and make some notes?
Well, I have from yesterday, input arrow pointing to the whole f of n that you wrote down. But
Mr. Kenneth.
you must be pointing to the end instead of the whole thing.
Well, so that might be a small mistake. So we need to be clear about this. But if you look literally over here, an explicit model relates outputs f of n to inputs n. It's been up there. All right, so we're relating inputs, which I will say this. You can say in or, does anyone know what the other input we typically use when it's continuous is?
X.
There we go. Right, so it relates inputs in or x, which you can use any input, but those are the two common ones. In or x to outputs. And so what would the corresponding outputs be? F of n and f of x?
Yeah.
Okay.
Yeah, it's starting to feel good in here now.
Well, I don't want Mona to be frozen, so I'm turning it down a little bit. So we're relating inputs to outputs. That way you can plug any input in and get any output out. A recursive only lets you go from the current to the previous, or from the previous to the current. So, the one nice thing is with an explicit equation it already has that starting point built in there. So, I do want to bring this up because this is important for the future. Recursive equations, can it be used with continuous or discrete models or both? An explicit equation, can it be done with continuous models, discrete models, or both?
Both.
The recursive can or the explicit can? There's already a hint built into the board right now.
Or,
To this board. There's a hint up here already.
May you repeat the question?
A recursive equation, can that be used for a discrete, a continuous, a discrete model or a continuous model, or can it be used for both? Same question for explicit. A continuous? Both? Okay. Let me ask you this, which input do we typically use for a continuous model?
Fn minus 1.
Are there any other inputs out there? X, right?
So is it explicit? Wait, never mind, that sounds good.
So we typically use X for what type of model, discrete or continuous? Okay, let's come back to recursive and explicit after we talk about continuous versus discrete then. What is a continuous model? What do we mean by that?
Only real numbers.
Does
Only?
continues between the isolated segments.
Okay, so there's a couple things. So here's the thing, Caroline, it's just a small thing on language. You say it's only the real numbers. Hey, listen. You say it's only the real numbers. However, what numbers do y'all know that are not the real numbers?
0.5.
That's a real number.
I don't know any, Mr. Jimmy.
8.
That is a real number.
It's a trick question.
You probably do, some of you might know some imaginary numbers. Say again.
F.
F? Well, that's a variable, not a number.
Well, how is A a number?
Well, E is known as Euler's number. It's the number 2.718281828, and then it continues after that. Forever without repeating or without terminating. It's just like pi is a number. Okay?
I like the compound.
Same. Compi is my favorite. Anyways, but a continuous model. But here's the one thing I want you to understand, Caroline, is I just wouldn't say only, right? With a discrete model, you could say it is only the natural numbers, because that's only some of the numbers that y'all know. And I will say the real number system is not the only number system out there, but the real number system is a lot of numbers. Any kind of decimal you know, any kind of radical, fraction, anything like that, you're talking about the real number system. But the continuous model, continuous models have domains on the real number system. I agree with that idea. And a lot of that is because of what McKay was saying. So McKay, what were you saying about isolated points? Or about points?
It continues between the isolated points.
Okay, so because the function continues between points with a smooth curve. And this might be where it's helpful to show some examples, right? Is this continuous?
Just discrete,
That's discrete right now. What can I do to make it continuous?
draw a line, connect the dots,
Connect the dots. Would it be with a line though?
with a curve,
Okay,
a curve.
with a smooth curve. Now, remember earlier how we were talking about a rectangle is, or a square is a type of rectangle, but a rectangle is not necessarily a type of square, right? A line is a type of curve, but a curve is not a type of line. Because a line is strictly defined as having that additive rate of change, right? A curve doesn't necessarily have to have an additive rate of change. Okay, so that's a good example though of a continuous. Would this go under continuous or under discrete?
It's neither.
Why neither?
It's not a smooth curve.
It's not a smooth curve?
It look like it's
It might be.
I mean, so there's a point here, point here. Does it have a smooth curve in between those points? What about between here and here?
Yes.
So even though it's cutting back and forth, is it a smooth curve? Yes? Are there a bunch of points there?
Yes.
So is that a continuous model? Is it continuing between any 2 points you could identify?
Yes.
Yeah. Well, I've only shown 4, but
There's like a million.
is there only a million?
There's like,
Or it could be more or less than that, but still.
It can't be less than that.
just let me have my
sorry.
weapons, man.
Here's a fun little fact. You see these 2 points right here? Those two? Anyone know how many points are in between those 2 points?
No, so there's infinite amount of points.
There's infinitely many points. The reason why, and this is legitimately true, the reason why there's infinitely many is in order to create that smooth curve, like I know I draw a point like this, but how big is a point really?
Microscopic.
Even microscopic doesn't quite do it. I believe, I believe, unless I'm wrong on this, Mr. Logan, correct me if I'm wrong, but a point doesn't actually have any size, right?
No, it has no, it's infinitely small.
It's infinitely small. So in order to actually build up enough to create that curve there, you have to have infinitely many of them to even create any kind of size.
My life is a
Sounds like
lie.
Ant-Man.
Yes. In some ways, I never would have thought about that when he goes subatomic, you mean? Goes into a realm that you cannot see when it's so small that it doesn't really exist, yet it still does.
Yeah.
It's kind of similar to that idea.
Then you get 8 by double.
But then he, what?
I've never seen a movie.
Oh, wow.
One, you need to see Ant-Man. Fantastic. But that's what's kind of happening there. That's what we want to recognize is, even though those two numbers are so close, those points are so close together, there's infinitely many numbers, or infinitely many points between them, right? So that's what's making it continuous. Remember how you said all real numbers? Hey, really quickly. Remember how you said all real numbers and we talked about the fact that it's on the real number system?
My mask gets hot, I have to let the air out.
You leave your mask on. Or otherwise there's no point in you wearing a mask.